Hi, my name is Rosara, and today I'll be discussing the third lab, the black hole. So the purpose of part 1 of this lab was to calculate the mass of a black hole by analyzing the net force on the star. For part 2 was to find the initial velocity needed for a ship to leave the planet's surface and successfully travel around a black hole without crashing into it by the gravitational forces of the planet and black hole. So a brief overview of the results of this lab is that the mass of the black hole was found to be 2.16 times 10 to the 34th kilograms, and for the second part, the initial velocity was found to be negative 4 times 10 to the 7th meters per second in the x direction and 3.8 times 10 to the 6th meters per second in the y direction. A couple of key physics principles used in this lab include Newton's second law, which is the net external force equals the change in momentum of a system divided by the time over which it changes. A couple of key formulas from this law was that net force being set equal to the change of momentum over change in time. This was also equivalent to the net force parallel and perpendicular components. This idea helped in estimating the overall force acting on the spaceship and planet, and which contributed to its direction of motion and position. The update velocity and position formulas were used to iterate the position and velocity of the spaceship and planet, and which was determined through the net force. Another key physics principle was the universal law of gravitation, in which force is equal to g times both masses over r squared times r hat. This helped in the calculation of the forces acting on the spaceship in part 2 and how it affected its orbit and motion. In these computational models, the system, which is the star in part 1 and also the starship in part 2, while the surroundings were the black hole in part 1 and the star in part 2. The initial conditions was that delta t was equal to 1 day, since that was supposed to be how long it took for the star to make one orbit, and in part 2 the star's mass from part 1 was entered to be 2.0 times 10 to the 30th kilograms, and the initial velocity was found and entered. And for both parts, the mass of the black hole was said to be 2.16 times 10 to the 34th kilograms. The assumptions were that only the black hole is acting on the star in part 1, since there are no other objects included in the scenario, and everything like air resistance is not included. Also, the black hole and the star are the only objects acting on the starship in part 2, since those are the only ones in the scenario which are said to affect the motion of the starship. When the given star mass was entered, as was the initial condition of the change in time, which was equivalent to 1 day, then the lines of delta V, delta P, net force, and etc. were set to the coinciding equations through Newton's second law and the universal law of gravitation. For example, the universal law of gravitation was rearranged so that the mass of the black hole was calculated for every point in time, with the previous values like net force and position of the star. So the mass was found through copying the iterated masses at each point in time through Glowscript, pasting it on Excel, and finding the average, which concluded that the mass of the black hole was approximately 2.16 times 10 to the 34 kilograms. Results in this experiment yielded that the mass of the black hole was 2.16 times 10 to the 34th kilograms, and the F net was equal to 1.027 times 10 to the 29th. And this can be connected to the sense that the universal law of gravitation's equation shows that the mass of an object is equal to the magnitude of net force times the magnitude of the change of position of the star squared over the mass of the star times g. So a larger net force would indicate that the mass of a black hole would also be larger. So in part 2, the mass of the black hole from part 1 was included, and the initial velocity of the starship was calculated through trial and error, in which the x component had to be negative and the y component had to be positive, and both had to be less than the speed of light. The universal law of gravitation was applied to find the net force on the planet and the ship, and the Newton's second law included the updated velocity and position formulas, which were used to iterate the position and velocity of the starship, which was dependent on the net forces of the star and black hole after the engine shut off. So in these results, it took multiple trial and errors, but the initial velocity was found negative 4 times 10 to the 7th in the x direction and 3.8 times 10 to the 6th meters per second in the y direction. This factored into how the starship would first go and how the forces of the star and black hole would affect the starship. The initial x velocity had to be negative and relatively small, so it wouldn't crash into the star, and so it would start off going the correct direction. The initial y velocity had to be relatively large so that it wouldn't go straight into the black hole, since the black hole's net force was relatively large, considering the universal law of gravitation. So a couple of sources of error in these computational models included that it doesn't account for other forces which could impact the direction and velocity of the planet and spaceship, so in reality it may be a little off, and also the trial and error method could have been more accurate in predicting the minimum velocity to get the spaceship as close to the black hole as possible without crashing. In addition, the mass found in the first part was an average, therefore it may be less accurate and affect the results of the second part of the lab. So the net force and rate of change of momentum components are relatively the same. However, the main difference is for F net, the mass must be known, while the rate of change of momentum can use velocity and position. Also, the net force is in the direction of the center of the circle of orbit, usually while the rate of change of momentum is mainly observed through its components and in the direction of motion, especially the parallel force, which is a key in showing the speed of the object. The initial velocity should have been a smaller magnitude of x and a greater y component. An initial velocity I found for this was -2 times 10 to the 6 in the x direction and 13 times 10 to the 6 in the y direction. This was due to the fact the spaceship had to start off in a more vertical path, and the smaller magnitude but still negative x velocity was to make sure it wouldn't crash into the planet or the black hole. And with that, thank you for watching.